My plan for today is to use enough dynamical systems and ergodic theory to motivate the problem, which will be about subshifts, and then from then on attempt to show the methods that we use to prove a current result, which rely on graphs, and then talk a little bit about what our current work is, which is some improvements we make, some refinements. So I should start by saying that everything that I've been doing has always been joint work with Michael Damron. So the context of our problem for subshifts is that we will always be considering a minimal subshift omega, which in terms of the language, which I use with the script L, it means that the language is bi-extendable, closed under factors, or subwords. And then the minimality condition here, which is a dynamical property, here just means that the language is uniformly recurrent. Right? So for any small n, there is a capital N, so that any factor of size small n is contained in every word of size large n. Right? And then I'm going to add the condition that to make this interesting, otherwise it's somewhat boring, is that it's aperiodic. Right? So all that means is if we consider the plane complexity function, one condition on that says that we are bounded from below by n plus 1 for all n. So this is just the framework that I'm always dealing with when I'm talking about shifts. So as has been mentioned a few times, we keep sneaking measures into the talk. So such shifts admit a convex set of probability shift invariant measures. And what we're going to be concerned with is the subset E, which are the ergodic measures. And I believe, as was mentioned before my arrival, these are the extremal measures. So in the convex structure, these are the extreme points. And the question that we'd like to know is how does the complexity affect the number of measures that we have in terms of the ergodic measures? And we'll talk a little bit about this just with some kind of a table over here, but how does the value of Pn over linear growth for large n affect the number of ergodic measures that we have? So in some sense, this is the right kind of question, because once you get past linear growth, so for instance, if this is infinity as n gets large, or goes to infinity in the lim inf, then you can construct examples where you have infinite number of measures. So the question becomes less relevant then. So what I will do then is I'm going to try to put things up here on the table, and I like to put them in maybe the right context. So the first thing that I'll mention came from Boscher-Nielsen in 1985. And he showed two different results, or at least I'll say showed with a fine print or caveat afterwards. He showed that if the lim inf of this ratio goes to a real number, then the number of ergodic measures is bounded from above by kind of a necessary but the floor of that value. So he showed that if you have this, you have a finite number of measures in particular. A slightly more refined statement is if you have a stronger condition, if the limb sup is equal to some real value that's finite. I mean, if it's infinite, then this still means the same thing. Then you get essentially an improvement by 1. Here I want to be careful because if this is, for instance, like Sturmian, then this would say we have no measures, but we always have at least 1. So I'm just covering myself. And what I'd like to say about this second result, I won't write it, is that technically Beauchamp showed this result for alpha primes that are less than 3. And he said at the end of the paper that this generalizes it generalizes to larger values, but did not explicitly state this. So then I think in 2010, Ferenczi and Thierry, they explicitly stated the theorem, but then I guess the proof was absent, right? For larger values. Your name is on it, right? Yeah. And then actually only last year, 2 people, Van Seer and Brian Acra, actually posted a stronger result a priori that actually finally proved this in writing. So it took about 30 years to have this written down completely in terms of just the statement of the proof. And what was maybe a motivation for this sort of problem is it comes from dynamics, and as I said, I will try to get dynamics out of the way as soon as possible so we can get to maybe more fun things. So the motivating example for most of this work comes from a dynamical system, or class of dynamical systems called interval exchange transformations. Right, these are piecewise orientation-preserving isometries on an interval. All it means is that you just take an interval that's by some convention like open on the right, closed on the left. You cut it up into a finite number of pieces, and then you just put them all back together by translation. According to some reordering. So this is the one I'm missing. So this is the type of map that we look at, but there's a natural way that you can encode this as a symbolic dynamical system. Right? What you do is if you give a name to each of the intervals, so A, B, C, D, then a point in this interval gets mapped to a sequence omega in a shift by omega I is equal to a letter. So I'm going to give a name to the letters just being little a, meaning part of this alphabet. If and only if, when I take the interval exchange map, which I will call T, I get that, in this case, depending on how you count, T of I minus 1 of x belongs to the interval marked by this name. And you do some formal things, like you close up the image of this so that it actually becomes a subshift, and you get some nice properties. And so that much I don't want to get into any more detail, but what I want to say, and this is part of the reason that I'm looking at these right now in this talk. Typically, for such shifts, the complexity function has a very specific form. When there are k plus 1 intervals, the complexity is kn plus 1. And it comes about because these discontinuities contribute for special words. And moreover, in this situation, it was shown independently by Katok and a period later by Veach that the number of ergodic measures for interval exchanges is bounded from above by k plus 1 over 2. The number of intervals divided by 2. And what I'd like to point out about this statement, though, is while these proofs are different, both proofs rely on some sort of geometry, meaning translation surfaces, associated interval exchanges, and symplectic forms that arise from this. So every proof that comes out of this, whether it was written that way or purposely written that way, relies on surfaces. So this is the only way that we know that this bound exists. And so that is what's going to end up being the bottom of my table when I do this correctly. And I want to remark here, which is going to be on this table as well, that examples that achieve this bound have been found for all values k. So this is sharp. The first example was by Michael Keen, 75, but it was specifically for, I'll keep with this notation, 4 intervals. And then it was extended to all k, at least in writing, by Yakos in 2010. So we know that this is the sharp bound, but again, this is, and I'll just kind of write here again, geometric proof, in case we drift off during the talk. Okay, so a sub-question then, which began with this original paper of Boschernitsen and has been unresolved since, is does a combinatorial proof of this bound exist? So this is kind of the motivating question that leads us to this. Can we get this same result, but can we do it through just properties of the shift, as opposed to appealing to higher dimensions, which makes me very happy. So on this way, there have been some generalizations. So Thierry wrote a paper, a note about some strengthening of this result by way of weakening the condition, but getting a very similar number. And so what we recently did with my co-author was we showed, motivated by this sort of condition here. So here's the theorem. If we have this eventual constant growth condition, so much like this, if for all large n, Pn plus 1 minus Pn is equal to some constant, or equivalently, I like this expression better. For all large n, the complexity function grows in a way very similar to this. And it has to be for sufficiently large k. The number of ergodic measures is bounded from above by k minus 2. So after 30 years, we have an improvement by 1. That's the first part of the story. And I should remark that the k bigger equal to 4 is needed in the proof, but also it does have to happen because if you put in, for instance, smaller values of k, then you should expect to actually get k minus 1. So, for instance, if k is equal to 3, we do expect to get 2 measures. It is possible. So it's not just an artifact of our proof, it actually is a real restriction. And to start with some open questions, this is just the first result we have in this area, but we have a heavy suspicion that this actually is not optimal. So that is the first thing. And then the second thing that we'll talk about then is a refinement. So it seems clear, if you believe what I've been saying so far, that the picture on the top left is an order of inclusion. So the top result, the top statement is true for interval exchanges. So we're kind of having an inclusive direction in our picture. So what we'll do is we'll introduce one more restriction. And so this is just a reminder for a word in the language is, and I'll use 3 different terms here, weak, regular, which in all fairness should be called ordinary, right? And strong by special. if the following two things occur. So if we look at the number of left extensions, so this is letters in our alphabet, such that when I extend a word to the left, it's in the language. And I'll just use a different letter for notation purposes. If each of these things, for us, will actually be 2. So, for instance, this implies that this is bispecial, right? Because it says if this is more than 1, it's left special. If this is more than 1, it's right special. But then we get this weak, regular, or strong if the number of two-way extensions, or bi-extensions, in this context is either equal to, it's weak if it's 2, it's regular or ordinary if it's 3, and it's strong if it's 4. So this is other than the fact that I misused the word regular for ordinary, these are 3 common terms for bispecial words in a language. And we will say that our shift satisfies the regular bispecial condition if all large bispecial words are regular bispecial. And I should remark, because I'd like to fit it into this picture, that there is a paper by Ferenczi and Zamboni in the London Journal from, I think, 2008. And it tells us that shifts that come from IETs satisfy the regular bispecial condition. It satisfies more, so this is just one property that it does satisfy. So we can correctly put the inclusions this way. So regular bispecial, a priori, is contained in here, and IETs are contained in here. And so then our result that we are working on now, claim, is that currently our best answer that we have is 3/4 K. And so I'd like to show that, in some sense, these results said everything was essentially the same order as the growth, and our first result that has an improvement has the same issue. This is in some sense morally halfway there, right? Between 1.5. And so the goal for the rest, like I said, is to try to avoid dynamical words for the rest of the talk, except for to set up context. And this is another to supply more open issues. We definitely do not, we hope it's not sharp, but we also don't have a proof either way. So I hope from here on out to not use direct dynamical terms before I move on to kind of how we prove this and then talk about that middle blob, or that middle result. So are there any questions so far? Just, the hope is if you're with me now, then we're still friends. We'll remain so for the rest of today. Okay. So the method that we do is highly motivated by the original paper by Boschernitsen, as well as Thierry's statements in his paper about the reliance on special words. And so to see these things in the way that we view them, at least, we're going to appeal to Ruzzi graphs. So I'm not claiming that this is our construction, obviously, but so just as a reminder, right, a Ruzzi graph is a directed multigraph, and for each n, the vertices are equal to the elements of the language of length n, right? And then the directed edges correspond directly to words of language of one size bigger, right? You have an edge if and only if a word of length n plus 1 begins with the first word and ends with the second, and that would make an arrow. So all we do first so that we can start drawing pictures that are a little less gross is that we just define special Ruzzi graphs. And here the difference will be the vertices will just be all special words of length n. And edges will be, and I'll say it without writing too much because I don't want to say it past this, but it's just going to be the paths in the original graph, and precisely paths that avoid special words in the middle. And just for one small technicality, it'll help us with counting later. If a vertex, which I'll now use instead of word, is bispecial, meaning left and right special again, we express this as two vertices in the special graph. And we do this in a, other than the fact about why we would even do this, the picture is not too bad. It's just saying, okay, so if I have maybe some subgraph of my so let's say that this is part of my picture of my Ruzzi graph. Then what we do is, well, here we have a right special word, so that will become an actual vertex in our special graph. And then here we have a bispecial word. So what we do is we split into a left and right component and connect it by an edge. And then all incoming edges to the bispecial word go into the left version of it, and then all outgoing words, or outgoing edges come out of the right special version. That's really it. So that's the most technical thing that we did with this definition. And I'd like to remark that under conditions like the regular bispecial condition, the number of vertices of our special graph is always 2k for all large enough n. So the number of vertices are fixed. This is one of the reasons why we wanted to do this technical thing of breaking up by special words, is that we can have a very specific count. Okay, so this is the part that I'm going to definitely wave hands over for the sake of the nature of this workshop, which is I'm going to express that we've defined a coloring, which is where probably most of the work came in, but I will not express how. We can obviously discuss it later, but so what we do is, because of this property, the fact that we have a finite number of these graphs, we then may find an increasing sequence of n's and fixed special graph, lambda, such that this is the graph that we see infinitely often. So nothing but just, pigeonhole, very harmless statement to say. And then on this, we define a coloring map, which we'll call by fancy C, which goes from this fixed graph that appears over and over and over again into the ergodic measures, which we'll consider to be colors, and then just a canonical symbol for not colored. So for people with backgrounds in graph theory, I must apologize and explain this is obviously a very non-standard coloring. Right? But it is a way of putting colors down, so I still think it's appropriate to say. And this particular thing we show, and this is all that we're going to use for the rest of the talk, is that there are properties that this coloring function must hold, or must have. So the first statement is, for each actual color, for each ergodic measure, there exists a left special vertex and right special in the graph that has that color. So it's defined in a way that no ergodic measure is missed. It has to show up somewhere in this picture. And then the second one, now I can actually start drawing honest pictures. If we have a particular vertex if we have an actual honest color, and either I'm trying to keep everything consistent. We have that this is a, well, obviously left or right special in our picture. If either of these things occur, just to lock down notation here, then the unique extension in whichever direction from W must share that color. And then at least one of the two branching choices must share that color. And so really this is what we do. I mean, we went through some work to show that, and I guess I should make clear, because this notation has been used many times this week, I mean the vertices, right? When I talk about the graph. So I'm keeping this up because this is somehow, these ideas are crucial to most of what we talk about. So what did this do? Well, this tells us then that if, for instance, in our original version of our proof, when we were trying to show k minus 2, we see that some structure arises if we have too many measures. So for instance, if by contradiction, we had, for instance, k measures. I should remark that, for instance, that first property tells us that every measure has to color at least 2 dots. There are 2 k dots, so k would be the maximum we would expect to see naively. So, well, what would actually happen? Then for each color, the vertices colored by this come in the form of exactly this structure. We have exactly one left, one right special by property 1. We have to have at least one of each, so that's how many we can have. And if we try to draw on the graph what this actually has to look like, we have this left special word. Its unique outgoing edge must go to V, because it's the only other thing that's colored by the same color. And so this agrees here. And moreover, they each have to have an outgoing or incoming edge that passes its color along as well. So this is what I mean by structure. If we have that our measure is too big, if we have that the pre-image of a color is minimal in this sense, we have a 2 loop. And it just follows from these two properties. So nothing past this. It's very, very naive. So for instance, let's say we continue with this contradictory thought, then really what a graph looks like would be just a bunch of loops connected in a circle. And each of these loops has their individual distinct color. And if that's all we could say, then we wouldn't say anything new, and we'd be done and somewhat sad. So what we do is we work on making something else, which is where we got stuck here for the, well, not stuck, but we needed to do this. So with a little bit of work, you find some kind of interlacing sequence of numbers with your original sequence. Remember the ends that defined our special graph lambda. You get this new base graph. And so you get a new coloring function on this new graph to the measures. And I won't say this in precision here, but C prime on this graph is related in a natural way to C on the original graph. And because we're talking about, the goal of this talk is to get to regular by special, I'm going to restrict a little bit to just loops and maybe say what I mean here. So I'm going to keep this. So the actual new graph that we had is related to lambda by bispecial moves. And so what do we mean? We mean that if you look at every value n that makes up a contribution to this graph, then somewhere between, for instance, nj and nj prime, you will encounter a bispecial word, and depending on the nature of that word, it'll change that local picture. So I don't want to say that, or definitely not write that, but I'm going to say for loops what's going to occur. So let's say we have this loop. And for the sake of right now, this is in lambda, let's say that in one of our base graphs, or our nj's, this corresponds to a bispecial word. We'll just call it u or w. Then moves here. So this is what it means that at each of these nj's, this is the picture that we have, or at least we can make it so that at each nj this happens. So those bispecial conditions that we mentioned before, weak, regular, and strong, well, these can correspond to certain choices here for what sorts of bi-extensions of u actually occur in the language. So in the weak bispecial case, what we have is that when we draw our new graph, so the plus is not subscript, right? In our new actual Roosie graph downstairs, we have 4 vertices. I'm going to draw the first one to suggest the idea, then after this I'm not going to draw the other ones. Okay, in the weak bispecial case, we have only 2 bi-extensions. So that means that, for instance, I can only draw 2 edges here. And because of the minimality of our graph, that means everything has to be two-way connected. So in the weak bispecial case, this is the only thing that we can have. So what that means is if you redrew this picture upstairs in lambda prime, that goes away. But what's important for us is that the color just has to move along this edge to the neighboring vertices. So the idea is it gives itself up, but then its color moves. So this is what I mean by relationships between C prime and C. In the strong bispecial case, you just draw the same picture, but now you connect all possible arrows. And when you redraw it in maybe a more legible way, you get what we're calling a tower. So the loop persists in some way, and then now there's a new base level down here. And I won't get into details about how the coloring is related, because we're not going to use it today. So I'll suppress this. So then the remaining two cases, which are the ones that we're going to focus on, are whenever you have regular by special, which means that you have 3 arrows to draw. And that means in this case that you have 2 options. You either draw the arrow up here or the arrow down here. If you draw the arrow down here, then you actually have one edge that comes in and leaves. And you have another edge that just takes a longer time to come in and leave. But the idea is that the loop disappears. So this is one option for regular by special. And this is actually, somehow for us, this is the ideal because just like in the previous case of color spreading for the weak by special, the color on these 2 vertices must stay. And now, because of how our rules work, because these 2 are colored, they force color out. So again, just like in the weak by special case, color spreads. And then I'll say it, and I'll wave my hand again, and then I'll just draw the picture, which actually won't be very hard. If we drew the edge up here, then what you see is you actually come in, and you have a loop again. It's just somehow moved around a little, but we have the same loop, and it persists. And the color has to stay exactly where it is. The color may not spread. However, the key thing about this is that by minimality, this sort of phenomena can't happen forever. Because what does it really mean? Morally, what's happening is all the words in our language that encounter this loop are just long words that enter, wind around, and leave. And so if we are persisting, it means that we still have a lot more windings left to do. And so by minimality, you can't wind forever. That's essentially the only thing that we need here. So these 2 are the 2 things that I want to make sure that we keep in our minds. But I'll just remark here that this sort of thing is what gets us the proof that we needed for k minus 2. So how can we see this, for instance, in the picture that I drew and then erased? Well, if we have our k loops, by this kind of argument, at least one of those loops at some point goes from that picture to this picture. So one of those loops has to give up and spread its color elsewhere, which is a contradiction. So this gets us, with a little bit of just being careful, our correct bound. So I'm transcribing just the 2 possibilities for regular by special, because now we're going to move to the newer thing, which is the middle box. And these are the only 2 possibilities, because in the regular by special condition, these are the only things that are allowed because we're taking an infinite sequence. So what happens at the beginning doesn't matter. And so here it seemed to be much easier to start getting better numbers because we just started making these observations, and they just kind of came one after another. So from here until I stop and let everyone leave, we're going to assume the regular by special condition. And now I can just draw pictures that don't have to have very many words. Under the regular by special condition, if you try to draw 2 loops next to each other, now it seems somewhat clear that if this is colored by one color, this is colored by another color, this can't happen. So now not only do we know about loops a little bit from our first case, but now we also know that under the stronger condition of the regular by special condition, loops cannot neighbor each other. And so under this condition, we may then naturally define a subset of the vertices in our graph, lambda, that belong to two loops. So everything that belongs to a two loop, we'll define it as an element of V2. So if there are that many measures that have loops, then there are 2 times that many vertices. And by this lemma, we can define, and we don't really care what letter we call it, phi today. There's a well-defined map going from these vertices and loops to anything else in the graph. And the way that we just say it is phi of w is w prime if and only if these are adjacent in the graph. And one way to say that they don't belong to the same loop is that they don't share the same color. So now we have a well-defined idea of just writing a name down for this, and it will just help us come up with a couple other sets. So then we may partition the rest of our graph into sets. We're just calling them WJ for now. 1, 2, 3. Where each of these sets is defined by how many loops is it adjacent to. So these are elements that touch exactly J loops. So the pictures here then are somewhat clear. There are no loops around an element, and I'll be agnostic about the arrows because they don't matter. W1, W2. And I'm going to keep these 3 up, but not the rest, or not the remainder, and I'll tell you why, because that's our next result. That's somewhat natural. So I'd like to comment, so we can just keep a tally before we have lunch. So already you can show that we get our first crack at a constant bound that's less than, actually less than k. Just from these, the non-neighboring is enough. So our next lemma is that that set that we just defined as W3 must be empty. So what does that mean? It means, this is why I reserved the picture so I didn't have to draw it twice, because if something was neighbored by 3 differently colored loops, then kind of by this process we mentioned here, at some point one of these 3 loops must give up and spread its color into the interior. But then if it spreads it to the interior, it must go along one of the other 2 edges and hit a differently colored loop. So for instance, if this is the loop that this occurs for, so let's say that this is the one that changes. So this changes from here to here. Then whatever this is colored by must pass along to this vertex. But then that color must pass along to one of these other 2. And by definition, these are all differently colored, so it's a contradiction. So it's very, very simple. Okay, and just to kind of help see our process, because this is a working process, this lemma now gives us that this is bounded from above by 8/9, which is smaller than 11/12. So then, the next observation is that with the abusive notation that everyone calls an abuse, but we all use it, so how is it an abuse? If we look at the color for any element inside of W2, so something that touches two loops, it must be not colored. And these are all very just kind of simple observations, right? So in the sense of once we see what this all means. So if you look at our 2 case, suppose that this is colored. By our rules, 2 of these edges have to pass the color along. We have an option for one, but not for anywhere else. So we're stuck. So again, by doing this and being very naive with counting, we now achieved this bound, which we thought was going to be the best for at least a little while. 5/6, again, less than 8/9. So then we finally get to the last statement that we have so far. And I'm going to write this as a claim because we're still writing down the proof correctly. And it's going to unfortunately be the most technical of these kind of results up here, but so if we have a color that colors more than 2 things, that's all we're saying. Then the elements that are colored by that color intersected with this set, things that do not touch loops, must contain at least 2 elements. So this is just an inequality, but all it's saying is that if you have a blob in your graph that's colored, and there is more than 2 dots that are colored by this, then at least 2 of those dots cannot touch a single loop. That's it. And with this being correct, this is what finally gets us to 3/4 K. And I'll just remark that I would write a lemma down and be more confident. We have a proof for bounded from below by 1. That much is very clear in terms of the proof. And if that was just the case, somehow it chops off just this factor again. So if we only had 1, then we still got better than before, but this is the thing that we currently are stating. I guess I'll just say where we need to get to and where the problem arises. So the issue is that there's kind of a hard bound that we can't get past without some more tools. So we kind of expect better. Than 2/3 K without treating properly 3 loops. So we basically, that's as far as we can go if we're going to be as silly as we can be and only look at 2 loops and make a lot of comments about these things. Basically, we can get this bound if, for instance, everything colors exactly 3 dots, then this is the bound that we would actually achieve. And so by a 3 loop, we just mean, again, I won't write the arrows down here, but I will write them around this. So it's a loop that contains 3 vertices, and somehow it becomes a little more subtle. Because, and I'll just briefly say why. People seem to at least believe me when I was talking about the idea of a loop. You know, you have one option. You enter, then you leave, right? The problem with 3 loops is that you can enter more than one way or you can leave more than one way. So the statements become much more complicated. And not only that, but I think there might be hidden in there some actual issue past just the terminology. So I guess I'll just close by reminding that I did, maybe quickly and maybe too quickly, but I did present open problems in the spirit of this workshop. So everything up here is unclear in terms of whether or not these things are sharp. In fact, we have very strong beliefs that even our top result can be very much improved. Because, for instance, if k was 1,000, you still have, I think, 992 of the colors have to be loops. So your structure is still very strange. But we just have not explored this quite yet. So thank you very much for your attention.
So you didn't say anything to the proof of the right uppermost blackboard. So everything depended on this, I think. Can you improve on that, or is this the result believed to be optimal?
So you mean this?
Yes.
So in some sense, there's really not much to improve in terms of the rules themselves. So these things basically are exactly what they can be. So for instance, there are occurrences where, for instance, for any dynamical system, or not for any, but you can construct them where every measure will occur at some point in the picture as a loop. So you can't make that better, just a priori. And these rules just follow from the definition, which I very cavalierly skipped this part, but it was helpful for us. The issue with this and the improvement is something that I didn't really make clear during the talk, somewhat on purpose, which is there's a technical issue that, in some sense, whenever I go from one graph to the next, I go from lambda to lambda prime, the way that we define our color is based off of some notion of density. And basically a positive density gives us a color. Every time I move from a graph to the next one, I can actually lose a little bit of color. So maybe if, for instance, this loop persists for a really, really, really long time, then by the end of it, I've lost it. And I don't know where it is anymore. I know it's somewhere. So part of the proofs that we kind of swept under the rug today on the blackboard is that when you have a two loop, for instance, you know that until that loop gives up, the color must stay put. So that's the part we need to improve, I think. Is like, for instance, that's the problem with a three loop. We'd like to say the same thing, that there's a similar notion of this thing sticking around until it stops. But then the proof that it actually keeps the color in the right way until it stops, that's the part that becomes a lot more complicated, even just for three.
Here you need that the complexity is linear. Because you might have very long paths between two spatial that you forgot and that may somehow carry some ergodic measure without being located to spatial, no?
Yes, so this is definitely, the way that we define this is definitely, so the question is if you don't have our top condition,
yeah,
right? What goes wrong? And certainly, so definitely the best that we can do with our coloring is still play some kind of game if this is finite.
Otherwise, you have to control the lengths of the passes. So
Yeah,
if they are
yeah.
super linear, then they might carry still some ergodic measure that, I mean, I don't see how, but it's not impossible. Because of this density thing.
Yeah, so we can't be as either you think of this as fancy or simple, I'm not sure, but we can't be quite like this if, okay, so what we can do is, part of these proofs, right, is that even if this condition holds, but this is infinite, there are plenty of times, an infinite number of times, where you're still, the actual complexity is bounded by a linear function. And you can still play the same game, but then you have to restrict your attention only to those times. And you're right, then the problem is you lose control in the middle. So there, we can, I think we can recover these statements, but we have to be very careful, is the problem. I can say that we can relax this condition just a little bit, right? But it's somehow exactly speaking to your statement. If the set of n such that p of n plus 1 minus pn is bounded from by k, if this is syndetic, for instance, so only bounded gaps, then the same mechanism up at the very top still holds. So it's a slight relaxing of our condition, but not much. Thank you.
Other questions?
Yes, can you tell us a few words about where the coloring comes from, or is it just too technical?
I say a few words, no. I'd be happy to talk about it though, but yeah. So Thierry can.
No, you can feel it in okay, you have your Grossi graph. You take so the colors are made by the ergodic measures. Okay. So you pick we saw on Monday, given one ergodic measure, you have always generic points. That is points for which the frequencies do right correspond. But a generic point is an infinite word. And an infinite word is an infinite path in the Rossi graph. Since you have finitely many spatials, one of them will be hidden with positive probability, with positive density, and even density larger than 1 over the number of guys. And this guy, when you hit so much, it will, even if you don't control what happened in between, it will give you enough frequency so that you ensure that it is the right ergodic measure, because the ergodic measures are mutually singular. And they form extreme points and things like this. So you have something like that says that somehow if you have some absolute continuity that says that here they must carry. Given this generic point, he will hit this special guy with a certain frequency, and then you put this as a color. So does it make sense?
Oh yeah, well, yeah.
I have one question, one or two actually. So do you have one example with k equals 6 where 4 colors would be possible?
This is.
I don't mean for measures, but so assuming that we know
right.
only this for.
Right. So the problem is that at least me and my co-author somehow we like paper too much. And so when you start trying to draw a picture for 6 and really enumerate possibilities, it gets out of control very quickly. We'd like to really sit down and just say, given these rules, what are possibilities for graphs with 12 or k equals 6 that actually could happen? And then maybe if we see an example where the pictures say this could happen, can we exclude this for some reason that we can maybe add to our conditions? But currently, no, we don't have an example. We actually would like to look at this under either just the constant complexity growth or regular by special. So it's completely open. That's just another thing to consider. Yeah.
Okay. And the other question is, so from the beginning, you assume that you consider only special factors with 2 extensions. Mm-hmm. Is there a simple way to exclude when you are on a larger alphabet more than 2 extensions?
Okay, so the only thing that we lose if so in the picture, so under regular by special, 2 happens. But actually, if you allow for more, so if you have more in and out branches, then these results are the same. So like, it would just be there'd be more arrows coming in and out, but the statements are the same. And so it doesn't need to be excluded necessarily. It's just that it just becomes, in particular, what happens is somehow by having too many branches, you actually lose how many vertices are on the graph, which makes our job easier, actually. So I guess to be clear, for instance, if there was a vertex with 3 outgoing, then now we actually have 2k minus 1 vertices in that graph instead of 2k. And it just gets better for us from there.
Okay. So I think there are no other questions. No? Who? I don't see. Okay, so we can thank Jon again.